Hi everybody, this is Dr. Frankie and I'm recording in and giving you this lecture from the airport in Florida today. So it might be a little bit noisy in the background. I want to apologize for that, but I'll do my best to give you a clear and concise presentation. In the last lecture we talked a little bit about site response for linear systems, and you're going to recall that the key assumption that we were making with those linear systems was that the soil dynamic properties, namely the shear modulus, the shear wave velocity, and the damping of the soil were not changing with shear. But we know from what we've learned from soil dynamic properties that they do change with shear. We've seen modulus reduction curves, we've seen damping curves that show how those properties are affected when we strain the soil in shear. So what we're going to do today is we're going to learn about two techniques that we can use for nonlinear site response analysis. The two methods that I'm going to introduce to you today are what's called the equivalent linear approach. And with the equivalent linear approach, this is the approach that we're going to use to essentially trick the soil or trick the analysis into thinking that we're dealing with a linear system, but in reality, we're not. The second approach is more of a brute force analytical method called the nonlinear approach. We won't get too deep into this, but just enough to have some basic understanding of it. And certainly on the homework that's assigned, you'll get to play a little bit with the nonlinear approach. First, let's talk about the equivalent linear approach. So with this approach, our idea is that we want to come up with an equivalent linear analysis such that we can apply the equations we learned from the linear approach from last lecture, but still account for the nonlinearity of the soil. So the overall goal of this equivalent linear approach is that we want to use a single combination of shear modulus and damping for each layer in our soil system that's going to represent the average shear response that we'd expect during the entire earthquake motion. So the whole idea is we're going to find the average modulus and damping value that we expect from the whole earthquake, and then we're going to plug those values into the linear analysis and spit out a single answer. So to do this, we're going to use our good old modulus reduction and damping curves. One of the things that we're going to have to deal with the equivalent linear approach is what we call the effective shear strain, and we denote this using this gamma sub F, EFF. What we've learned that the modulus reduction and the damping curves are typically determined in a laboratory where we're applying cyclic loading to the soil. So that's going to be like nice cyclic harmonic loading that's going to look something like this. And yeah, you get the idea. The problem is that this isn't the way that nature loads the soils. Instead, nature loads the soils like this curve using transient ground motions that are going to look like this. So the challenge, of course, is how in the world do we make the transient stuff look like or convert it to an equivalent cyclic motion? So what we're going to use is we're going to use this effective shear strain to convert the transient shear strains to an equivalent harmonic shear strain that would be equal to what we might see in a laboratory event. So the idea is if we have this transient motion, we can compute the amount of energy that is produced by that transient motion, and it should equal something that's a little bit lower or less than what we'd see with cyclic harmonic loading that has the same peak as the transient, but the area under the curves should be just about the same as it would be for the transient motion. So relationship has been proposed by Idris and Son in 1992, where we can compute the effective shear strain as some function of the maximum shear strain. If the maximum shear strain from our transient motion is, say, that guy, then what we need is this factor to multiply by our maximum shear strain to get this equivalent shear strain. So the Idris and Son proposed this relationship right here. That's a function of earthquake magnitude. So for a magnitude 7.5 earthquake, what we get would be a factor of 0.65, which is pretty standard. But if I have a larger magnitude, meaning a longer duration, more energy, then I would expect that factor to be a little bit higher. So here are the procedures that we're going to use for our equivalent linear approach to trick the analysis into thinking we're dealing with a linear system. The first thing we got to do is we have to plant some seed values of shear modulus and damping. So I say, you're going to guess initial values of it. You're just going to plant some initial seed values. That's really all we're doing. Then what we're going to do in step number 2 is we're going to perform a linear site response analysis for our layered system using a program like Shake or Shake 91 or ProShake, and we're going to obtain the shear strain time histories for each and every layer. So that's going to be this kind of stuff where I have time and I have shear strain, and it's, for every layer it's going to look something like that. So from that I can pick off my maximum shear strain, and then I can compute my effective shear strain and get an equivalent harmonic shear strain from that's going to correspond to the effective shear strain. That's going to be step number 3. Okay, so once I have the effective shear strain for every single layer, the next thing I want to do is I need new estimates of shear modulus and damping. And I want to go to the modulus reduction and the damping curves to get them. So I'm going to go and I'm going to plug in the effective shear strain that I computed, and I'm going to pick off from those modulus reduction and damping curves the new values of modulus and damping. And then I'm going to plug it back into analysis, and I'm just going to loop steps 2 through 5 until what's going to happen is I'm going to converge on values of modulus and damping. They're not going to change anymore. Once I converge, then I know I have a solution. And so doing this approach, we're still taking advantage of the numerical rapidity of the linear approach using the direct solutions. It's very fast, very easy, and all we're doing is iterating over and over and over again until we converge on the correct values that represent an average response from our soil from the earthquake, and then we can get our final shear strains and then time histories or whatever else that we want. So I have here a graphical procedure just to kind of show. Let's assume at point number 1, that's going to be my G value. Oftentimes this may be G max. As you can see in this value, it certainly is. And then I'm going to guess some initial value of damping ratio as well. So then I'm going to plug those in, do my linear analysis, and I'm going to get my max shear strain for my particular layer, and then I'm going to get my effective shear strain for the layer as well. And then from that effective strain that I get, I'm going to come down and I'm going to come over and get the corresponding value of shear modulus that corresponds with that shear strain. And the same thing with damping. Okay, then I'm going to plug those back into the linear relationship, and all I'm going to do is go around and around and around and around until eventually I'm just going to converge on a solution. You see how we're just getting closer and closer until eventually we pop in and we meet our tolerance levels, and then we say that we've converged on a solution. So the thing that makes the equivalent linear approach work is the fact that we are iterating. And through that iteration process, we're tricking the linear analysis into thinking that we have a linear system. Now, remember that this little example here is for just one layer in the model. We'd repeat the same procedure for every single layer of interest in the model. Before I move on to something, I want to emphasize here, you don't need to do this manually, and that's the beauty of the approach of this. When you do an equivalent linear approach, the software is going to do the work for you, and instead, all you need to do is specify that you want to do the equivalent linear approach and specify your tolerances and import your modulus reduction curves and your damping curves, and the software is just going to iterate until it reaches your desired tolerance and do the work for you. So that's the good news for you guys. Okay, so you'll recall in the last lecture I introduced this idea of deconvolution. So the idea is with deconvolution is I want to take a ground motion that was recorded on the ground surface, maybe on soil, and say that it was recorded on soft soil over here at one site. But say I'm interested in another site at a different location that has a different soil profile, but maybe similar rock properties as the rock that was beneath this strong ground motion. So the idea is, what if there was a way that I could use equivalent linear to go down through the soil to compute what the response would be at the bedrock, and then take that bedrock motion and apply it as the starting motion at a different site, and then run equivalent linear back up to compute the ground motion at the top of the ground at another site. That's the whole idea of deconvolution. So, I mean, essentially, we talked about the advantage of linear approaches is that you can go both ways. You can go up and you can go down. So a lot of researchers for a lot of years used deconvolution because we had a lot of recorded ground motions on soil, but we don't necessarily have a lot of recorded ground motions down at the bottom of the soil on the rock. That's really hard, if not impossible, to do. So deconvolution, in terms of what's going on in the frequency domain, we're working backwards. This time we're starting with a ground motion at the top of the soil. We're computing our transfer function, and instead of multiplying by our transfer function, we're dividing by it. So when we divide by the transfer function, ideally we're going to get the Fourier spectrum at the bottom of our soil profile, which would represent the rock motion. And then we can apply that motion theoretically as an input motion for another site that has similar rock properties. Here's the thing. You have to be careful when we use deconvolution, because there's a lot of different things going on in the soil, like large strain effects, resonant frequencies, basin effects, and reflections of waves that aren't modeled necessarily in the linear response analysis, but are going to come through as potentially spurious resonances. So a lot of these things, 3D effects, basin effects, wave reflections, those aren't going to be accounted for. They're just going to get fudged in to that transfer function that we're going to compute. And so the observed ground motions are not all produced 100% from soil amplification. A lot of those observed ground motions are coming from local site effects, like we talked about a few weeks ago. So what then happens? What's the danger of deconvolution? Well, here's something to consider. What would happen if we had a really high surface acceleration And at that same period where we had that high surface acceleration in the Fourier spectrum, what if we had a low value on our transfer function? So we're taking a high acceleration and dividing it by a really low value on the transfer function. So what happens when you take a big number and divide it by a small number? That's right, you get a really big number. So what we're saying is we may get a super big bedrock motion that is no way realistic at all. And then the danger would be, what if we take that motion and just blindly plug it in as an input motion in another site response analysis and run that motion up through the soil? We could be predicting crazy ground motions that aren't realistic whatsoever. So I'm really not a big fan of deconvolution. I say don't even use it, don't even bother with it. So what do I do? Well, rather than using deconvolution, I'd say me and most other professionals, rather than using ground motions that were recorded on the soil, we like to use ground motions that were recorded on bedrock. So these are what we call rock outcrop motions. So if I can get a ground motion that's recorded on outcrop, what I can do then is I can assume that the rock is going to be the same down at the bottom of the soil, and I can apply that rock outcrop motion as input at the base of my soil profile. I just have to specify in the site response software that I'm dealing with an outcrop motion so that it can correct for the free end wave effects. You'll recall that on the free end of a rod where we have a wave going through it, the amplitude is 2 times the incident amplitude. So we have to account for that if we're using these outcrop rock motions. But if we do that, then we get a lot more realistic answers, a lot more realistic ground motions. And studies have shown in the last 10 years or so that doing this practice, it actually does better in predicting the actual accelerations and ground motions within our soil profile than deconvolution does. So again, I prefer just stay away from deconvolution. But I guarantee if you get into this line of work, you're going to come across engineers who use deconvolution and use it routinely, religiously, and they're going to swear by it. So you kind of have to be careful there. You don't want to step on any toes. And again, this is the key. When you plug these things into their software, please make sure that you specify that the software, excuse me, or that you specify to the software that you're dealing with an outcrop motion. Okay, so everything we've talked about is the equivalent linear approach. Now we're going to talk about the second method that we can use to account for nonlinearity of soil in a site response analysis. Now this approach is much more complex than not the equivalent linear, but it's starting to gain a lot of traction and it's becoming more and more popular and easier to use. This approach is called the nonlinear site response approach, and what this does is we're going to actually integrate and solve that big nasty wave equation. And we're going to integrate it and solve it numerically in a series of small time steps, little delta t's, using a lot of different methods. The most popular is just this forward difference approximation method. So it's like the finite difference method. And so we're quite literally just time stepping our way through increment by increment through the time history, layer by layer by layer in our soil profile, and just brute force solving the wave equation. But one of the most important aspects of the nonlinear approach is how it models the stress-strain behavior of the soil, how it models the constitutive model. I'm also going to add in here how it handles pore water pressure. Because pore water pressure is going to change as a function of the soil shear strain. And so, and also the soil type and the relative density and the confining stress and all of those things. And so you need, hopefully your constitutive model will incorporate some sort of pore water pressure generation model. So let's talk a little bit about a popular way that constitutive models define how the stress path or the stress strain path works. We call these loading and unloading rules. Loading and unloading rules refer to if I have strain and I have shear stress. If I load up and strain a soil and then I reverse direction and I want to come back down, is it going to follow the same path? Is it going to follow the same path down, or is it going to come down at a different stiffness or a different slope of the line? That's what we call loading unloading rules. So one of the most popular and most applied methods of loading and unloading rules is what we call the Masing criteria. And here are the rules that define just the basic Masing criteria. So the idea is that if we're loading something for the first time, the stress strain curve is always going to follow the backbone curve. So if I go back to my little plot here, let me erase some of this. The idea is if I'm loading something, a virgin soil for the first time, I'm going to have this backbone curve that you're going to recall that we can get from our modulus reduction relationship or our modulus reduction curves. So if I'm loading this soil up for the first time, whatever strain I go to, I want to pause for a minute. Hold on a second. Oh, she stopped talking. Okay. So I'm going to load it up, and wherever I stop, it's going to be right on the backbone curve. And if I go the other way, wherever I stop, it's going to be right on the backbone curve. Now, if a stress reversal occurs, meaning I just change the direction of my shear stress, then the stress strain curve is going to follow a path given by this function right here. So in other words, the unloading and the reloading curves are going to have the same shape as the backbone curve, but it's going to be enlarged by a factor of 2. So it's going to come down with the same shape, but just a different slope, basically, a slope that's defined by a factor of 2. And then if the unloading or reloading curve is going to exceed the maximum path strain and intersects the backbone curve, then it's going to follow the backbone curve again. So once we get into virgin strain territory, then it's back to the backbone curve. And then finally, if unloading and the reloading curve crosses an unloading or reloading curve from the previous cycle, the stress strain curve will follow that from the previous cycle. So, let's just look at an example here. Let's start at point A, and let's say, okay, I'm going to load this up for the first time. So I'm going to load it up, load it up, and it's just going to follow the backbone curve. Now let's say there's a stress reversal at point B. Okay, since we're coming the other way, it's going to follow the same shape of the backbone curve, just going the other way, and it's going to be stretched out by a factor of 2. So it's just going to come back having the same shape, just going the other way, until we have a stress reversal, and then it's back to the backbone curve. Okay, then if I change directions, let's say I want to take it all the way to D. So once I hit the backbone curve, I'm just going to follow the backbone curve until I change directions. Then once again, as I change directions, it's going to be the shape of this backbone curve just multiplied by a factor of 2 coming back the other way until I hit and intersect the backbone curve again. Then I'm just going to follow it until I reverse directions. And if I stop and reverse directions again, what's going to happen is I'm just going to follow the same shape of the initial backbone curve, but it's just going to come up. And so you get the idea. So these are what we call the Masing criteria for loading and unloading. And so a particular constitutive model may follow the old Masing criteria, but understand that there's like a dozen or more modifications of the Masing criteria that are all based on laboratory testing, numerical modeling, or I should say they're usually based on laboratory testing and then applied to numerical modeling. The whole point is, and what we're really after, is we want to be able to predict this type of behavior with these Masing criteria, where we're predicting actual shear stresses and corresponding shear strains with time. So that's pretty powerful if you think about it, and if we can actually learn how to predict it correctly. So, like I said, we're not going to get very deep into the nonlinear procedure, but I just wanted to give you a taste for it. So here are the general steps that we would apply for a nonlinear integration analysis. In step number 1, we're going to start our time step. And what we're going to do is we're going to take the particle velocity and the total displacement are going to be known at each layer boundary. And at time equals 0, then of course those values are equal to 0. So we know our initial values at the boundaries. Step number 2, we're going to use the particle displacement profile to compute the shear strain in each layer. In step number 3, we're going to use our loading or our unloading rules, so like our Masing criteria, to, with whatever our time step is, compute what the stresses and the strains are going to be in each layer, and make sure that we have compatibility at the boundaries and those kinds of things. Then we're going to increment the time step in the ground motion at the base of the model, and then we're going to work our way from the bottom of the model all the way to the top and compute our stresses and our strains at each layer boundary until we get all the way to the top of the model. Then we're going to increment our time step, start at the bottom, and do the whole process over again and repeat steps 1 through 5 until we've worked our way through the entire time history. So you can see that this is a pretty sophisticated, complex procedure that we're going to apply. So let's go ahead and compare these two methods, equivalent linear versus nonlinear. So think of this as like celebrity death match. We've got equivalent linear in one corner, we've got nonlinear analysis in the other corner. Which one's better? Which one's going to win? Well, let's go ahead and have them go head to head. The first thing we notice is that equivalent linear, and I'm just going to call it EL to save space and time. So equivalent linear can lead to what we called spurious resonances at certain frequencies, and that's because the transfer function, we're assuming that all of the ground motions at the ground surface are due principally to site response, but we know that other factors like local site effects, like basin effects, and those kinds of things are going to play a role too, but we can't account for that in the analysis. So we get spurious resonances in our transfer function. These resonances usually will not occur in the nonlinear analysis. So I would say, for that point, the winner for that point is definitely going to be nonlinear analysis. Okay, in the second round here, equivalent linear requires that we use this kind of fudgy effective shear strain. And remember, the effective shear strain is this fudged equivalent harmonic shear strain motion that's supposed to be representative of the actual transient shear strain motion from the earthquake. And that's really sketchy, okay, when we do that, because they're two totally separate things. So we have to use that effective shear strain to ensure compatibility between the field and the lab results, while instead the nonlinear analysis, on the other hand, just directly computes the shear strain. So we don't have like a middleman. We don't have to use some sort of fudgy effective shear strain. We just solve the wave equation directly and directly compute the shear strain for each boundary and each soil layer at each time step in the analysis. So I would say again for round number 2, the winner is going to be nonlinear analysis. Number 3, equivalent linear is certainly much more efficient computationally than nonlinear. Equivalent linear computers can solve in a snap. Nonlinear, it usually has to step through and compute things step by step and requires a lot more time and a lot more computational effort. The interesting thing is, though, equivalent linear, and this is really important, I hope that you're paying attention to this. Equivalent linear does not solve the problem in a time domain. Equivalent linear is a frequency domain solution. So it's not stepping through time steps. It's solving the solution in one single calculation by multiplying or dividing, if you're deconvolving, the Fourier amplitude spectrum by the transfer function. And so, conversely, the nonlinear analysis, we're solving this in the time domain. So, this one's kind of a draw, because I would say even though that equivalent linear is a lot more computationally efficient, the fact that nonlinear is staying in the time domain is kind of desirable. And so I would say for round number 3 we have a draw. Okay, round number 4. Nonlinear analyses can be formulated in terms of effective stresses if we have a pore pressure generation model. Guys, I cannot tell you how cool this is. I can't convey my passion and excitement for this to you. Equivalent linear analysis cannot account for pore pressure generation, the development of liquefaction, and severe softening or softening of liquefiable soils, or say like quick clays, or the failure of quick clays from earthquake motions. It just can't do it. There's no mechanism in there to account for the generation of pore pressures and a drop in effective stress. But the nonlinear analysis can have a pore pressure generation model in it. It's a function of strain in each soil layer. So because of that, I say, man, this is a big win in round 4 for nonlinear. We can actually predict the onset of liquefaction in soil layers just through a time step analysis. So far we're through 4 rounds, and so far it is a slaughter in favor of nonlinear analysis. Round 5. Nonlinear analysis can account for site response effects of liquefied soil if we have a good pore pressure generation model in there. So in other words, think of it like this. Here's my ground surface, here's my bedrock, and I shake my bedrock and I send a time history up through the soil. Now what if I had a soil layer in here that was liquefied during the analysis? If that soil liquefied during the analysis, the shear modulus is going to plummet. The damping is going to skyrocket. And because of that, if I have high frequency stuff, the second it hits that liquefied layer, it's going to damp out, or it's going to filter out all the high frequency stuff, and the only stuff that's going to get through is going to be the low frequency, high period ground motions. So it's going to affect, if I'm trying to predict what my motions are going to be at the ground surface, then having this suddenly softened soil in my profile is going to make a huge difference. We cannot account for that in equivalent linear, but we can in nonlinear as long as we have a good pore pressure generation model. So once again, round number 5 goes to the nonlinear analysis. Round number 6. Nonlinear has the capability of modeling dynamic behavior of soils with very large strains if we use a good constitutive model. So in other words, if I go back to this example right here, and in fact we'll even get rid of the liquefied soil. If I have a little small earthquake or a small ground motion I'm putting in here, I'm going to expect that my strains are going to be small. And if I have small strains, then equivalent linear, if I look at my modulus reduction curves, and I look at my corresponding damping curves, if I'm dealing with really small strains in the soil, the change in, you know, that change in shear modulus and this change in damping, it's going to be really small. And so equivalent linear is going to give me a great solution. I'm going to have a really good solution that I can rely upon. But if I come in and instead shake it with a big motion, and I'm going to get some really big shear strains in the soil, well, I mean, just think what we're doing, right? If I come in and I apply a really big shear strain to the soil, well, now all of a sudden, I have a really big change in my shear modulus, and I have a corresponding really big change in my damping. And so when I remember with equivalent linear, I'm trying to do this iterating approach, right, where I try to zero in on a solution. If that strain is too big, then the equivalent linear approach is going to give me some really wonky values and stuff that aren't really going to be realistic and I can't trust. So, you know, in my personal opinion, and I know in the opinion of many other engineers, if you get strains that are larger than about 1% in equivalent linear for any layer, don't trust the solution. Just don't trust it. The strains are too large. I see a lot of people come out and they run equivalent linear, and you look at their shear strain plots and they have some shear strains in the soil that are like 3, 4, 5, 6, 10% induced in the soil. And it's like there's no way that equivalent linear solution is valid or realistic. So if you can keep your shear strains below about 1% for all your soil layers, or at least most of them, then your equivalent linear is going to be pretty good. Otherwise, the nonlinear is going to be probably your better bet. But the key is you have to have a good constitutive model that can give you realistic stresses and changes in stresses when you apply large strains in the soil. So again, I'm going to say round 6 is going to go to the nonlinear soil. So man, this is turning into like a really bad Rocky movie now. But here's the problem, and just like in Rocky, you get to the final round, and the guy who's winning the whole round, the whole fight, lets his guard down, and Rocky ends up winning, right? Well, here we are in round 7. In order for nonlinear to have all of this good stuff, you need a good universal constitutive model for the soil that's reliable and that is predictable and that gives you good values for multiple types of soil. And you also need a good and reliable pore water generation, pore water pressure generation model to go with that constitutive model. Now, a good model that we can just plug and chug and throw in and run with doesn't exist. No matter what people say or what they try to sell you on, it doesn't exist. what we can do is we can take a model, and if we have some site-specific testing, like from a laboratory test or like a centrifuge test or something like that, we can calibrate a constitutive model to match the dynamic properties of our soil, and then that nonlinear analysis is a lot more believable and reliable. Folks, the key to nonlinear analysis and using it is you have to calibrate. You cannot just plug numbers into a nonlinear model, run with it, and trust them or believe them. Unless you actually calibrate your nonlinear model against proven and validated testing data to validate your constitutive relationships, your nonlinear model is garbage. If that's the case, well, the 7th round is going to equivalent linear. Oh, hold on a sec. Okay, sorry about that. Here we are, round number 8. Differences in results between equivalent linear and nonlinear analyses are going to depend on the degree of the nonlinearity. If I'm dealing with low strains in the soil, like less than 1%, if I have a really stiff soil and or weak ground motions going into the soil, there's going to be no difference between equivalent linear and nonlinear. And for those cases, I would almost always recommend the use of equivalent linear analysis. For cases where the strains are larger than 1%, nonlinear analysis is going to be better if you have a reliable and validated constitutive model and a reliable and validated pore pressure generation model. So I would say in this round we probably have a draw. So the final synopsis, even though I gave something like 6 of the 8 rounds to nonlinear, and 2 of the rounds, or actually I guess 5 of the 8 rounds to nonlinear, 2 of the rounds were a draw, and only 1 round went to equivalent linear analysis. Guess what? Most engineering professionals are going to choose the equivalent linear method for most applications. And it's certainly a correct choice if we're dealing with low strains, stiff soils, and or negligible pore pressure generation in the soil. In my opinion, nonlinear analysis should be the method of choice if you're dealing with strains larger than 1% in the soil, soft soils, or potentially collapsible, quick, or liquefiable soils, and which would also be impactful pore pressures. So here's the deal. Why do you think practicing engineers or engineering practitioners are going to use equivalent linear analysis about 95% of the time in engineering practice? Why don't you stop and just think for a moment why you think that is? I bet it's not going to be too hard for you to come up with an answer. Okay, hopefully you paused and you thought for a minute about it. I'm going to give you my opinion. Equivalent linear analysis is fast. It's been around for a long time. Generally, we don't validate it, or we don't need to validate it, because we're relying upon modulus reduction curves that have already been proven and tried in the laboratory. And because engineers don't know what in the world they're doing. And that's a dangerous combination. So the majority of engineers in practice today are going to rely upon equivalent linear site response analysis. And now look, I'm a fan of equivalent linear, don't get me wrong, but I see it used in too many scenarios, too many of these scenarios here that I'm circling. And it shouldn't be relied upon in those types of scenarios to predict strains. Now, we can use them in those types of scenarios for other things, like to compute what we call cyclic stress ratios for liquefaction analysis. You don't know what that is. We're going to talk about it in a few weeks, but cyclic stress ratio is the way that we characterize seismic loading when we perform a liquefaction analysis. If we're using it for that kind of purpose, then it's probably okay. But if we're using it to predict actual strains, deformations, accelerations, velocities, the deformations is the same as displacement, right? If we're using it for those purposes, we should be using nonlinear analysis more, in my opinion. So anyway, to get you started and introduced to some of these procedures, I want to make available to you a copy of the software Deep Soil. Deep Soil is really powerful because it has both equivalent linear analysis in it and non-linear analysis methods as well. And it's user-friendly. And for your homework assignment, all you're going to do is go through the user's manual, which sounds easy, but it does take some time. And then there's going to be some tutorials in the user's manual that you'll need to complete and print out the output and the results. And you'll turn those in as your homework for the week. So with that being said, I think I'll end the lecture. I appreciate your attention, and that about does it for everything we're going to talk about with site response analysis. So if you have any questions, feel free to let me know. Contact me, get in touch with me, shoot me an email, come see me in office hours. I'll be happy to help you. So appreciate your attention. Have a great day.